In this module, we are going to see several examples of metric spaces. Please keep these examples at the back of your mind in the future modules where we'll see a number of concepts defined. First example, example 1. This is the example with which you are most familiar because we spent a considerable amount of time in Real Analysis 1 studying this example. This is the set R, the real numbers, with d of xy by definition just being modulus of x minus y. Okay, now we have already verified all properties needed in the definition of a metric has already been verified. In the chapter where we defined took an axiomatic approach to the real numbers, we had defined what this absolute value function is and also checked all these properties. Now, example 2 is one of the most important examples and also the most pertinent one when it comes to this course on multivariable real analysis. This is the set Rn n greater than or equal to 1 with d of xy defined to be the usual distance between 2 points in Rn, which is nothing but given by the formula under root summation I equals 1 to n xi minus yi the whole square. Okay, where we have written the point x as x1 to xn and the point y as y1 to yn. So this set Rn along with this metric is called Euclidean space. Okay, so before that we have to check that that definition in fact satisfies all the three properties of a metric space. The only thing that's difficult is the last property. So let me just make a remark that the last property or the triangle inequality, that is triangle inequality will be checked in the future. What we will do is we will study one general class of metric spaces that come from a norm, or rather come from an inner product, and there we will prove the famous Cauchy-Schwarz inequality. And this fact that the triangle inequality is satisfied by the definition square root summation I equals 1 to n xi minus yi the whole squared will follow immediately from the Cauchy-Schwarz inequality. So we will do that at a later stage. So with that being said, Rn with this metric d, with this metric is called Euclidean space. And this d that we have defined, the metric is usually called the usual metric. Mathematicians, as we have seen, are not very creative when it comes to terminology. It's called the usual or Euclidean metric. There are other natural and useful metrics that we can define on the space Rn. We shall see that in this module on normed vector spaces, which will come down the line. Okay, so this, as I said, is the most important example when it comes to our course on multivariable real analysis. Now I had remarked that this definition d of xy defined to be under root summation I equals 1 to an xi minus yi the whole squared is the distance between x and y, the usual distance. Can you figure out why this is the case? At least can you figure this out in R2 and R3? Please do that as an exercise. It's a very, very useful exercise and it will ground this theory in something concrete. Now, let's move on with more examples. The next example is really trivial, but it's very useful when you have some conjecture in mind and you want to get a quick counter example for this conjecture. So, this is called the trivial metric space. Okay, this metric space is defined as follows. Let X be any set. Let X be any set and define d of xy to be 0 if x is equal to y and 1 if x is not equal to y. Okay, so this metric is known as the discrete metric. And this metric space X with this discrete metric is often called the trivial or discrete metric space. This is a very trivial scenario, but it is very useful if you want to get a quick counter example to some naive conjecture that you make. Now let's move on away from this trivial example to the most important example in most of analysis, which is going to be a collection of functions. So next example 4. Let X be any set. Again, we are going to define a collection of functions defined on X. So we say a function f from X to the real numbers is bounded if supremum modulus of f of x as x runs through this set X is less than infinity. Okay, then we consider this collection B of x comma r. What is this collection? This is the collection of all bounded functions f from X to the real numbers. So take any set X and consider the collection of all bounded functions defined on this X. We define norm f. This is read norm. The norm of f to be nothing but supremum of mod fx as x runs through X. Okay, this supremum will obviously exist because we are taking only bounded functions. And given f comma g in this collection bxr, we define d f comma g by definition to be nothing but norm f minus g. Okay, now obviously because f and g are bounded functions, f minus g is also going to be a bounded function, and this norm of f minus g makes sense. Now check check that this example satisfies all the properties needed to make this into a metric space. It's rather easy to check. The only non-difficult thing is the triangle inequality, which itself is not actually difficult. It's quite straightforward. So we will spend a considerable amount of time analyzing this particular metric space. It's going to take up most part of an entire week of our lectures. Also observe that this example subsumes the previous example. Can you figure out how this example subsumes the previous example? Please do that. So nomenclature, this norm is called, I should mention what a norm is. We shall study normed vector spaces, which are vector spaces with an additional structure given by a norm. Okay, so this particular norm that we have is called the subnorm. And this metric is called the subnorm metric. Again, mathematicians are not very creative when it comes to terminology. This is straightforward terminology, just coming from the fact that there is a supremum involved in the definition of the norm, and that particular norm is involved in the definition of the metric. So as I said, what is a norm and why these norms are important will come at a later stage, not so far away, just maybe a couple of modules down the line. You will see normed vector spaces and inner product spaces in quite detail. They are the most important examples of metric spaces, and this concrete example BXR is by far the most important. So we have a small collection of examples at our disposal. More general examples will follow. With these examples at hand, let's move on and define all the basic concepts that you have already seen in the chapter on taste of topology and generalize those concepts to the setting of a metric space. This is a course on real analysis, and you have just watched the module on examples of metric spaces.